Hello everyone, my name is Chandra Sukanya Nandyala and I am the author and presenter of this paper which is named AUV Aided Isolated Subnetwork Prevention for Underwater Sensor Networks. So before we are going to see what this paper has contributed for underwater sensor networks, I would like to give some introduction about underwater sensor networks. Why do we need? So it is basically to observe the underwater environments and for underwater data collection, monitoring, navigation, sampling collection, and disaster prevention, and to assist in navigation. So all these applications of underwater sensor networks. We use acoustic communication, but acoustic channel has plagued with several issues which are like long propagation delay, and it has shorter bandwidth and higher bit error rate, and more importantly the sensors which are underwater sensor nodes are energy constrained, which are limited, very limited in energy because they contain battery. It is very difficult to replace or recharge these underwater sensor nodes. So when we model something for underwater sensor networks, we need to keep in mind all these issues. The communication between the sensor nodes and to the sink happens via multi-hop communication. So here, if we see this set of underwater sensor nodes as a connected and undirected graph as shown here, um, but a depth of the certain special nodes, which is 4 and number 5, can cause the network division as the main network, which is this above network, which is connected to the sink. Even their 4 and 5 depth cannot stop 2 and 3 to send data to the sink, but if 4 or 5 dies, it is like there is no way for the nodes 5, 6, 7, 8 or 7, 6, 7, 8 to send its data to the sink. So this is the problem that we are in this paper we are trying to solve the issue, so that all the data collected from the underwater sensor nodes can able to be sent to the sink for further analytics. So this is our network model where we divide the sensor nodes into different layers, which is hierarchical level here. The sensor nodes only send data from its level to the only higher level nodes, but not lower level nodes. So only the data will go only upwards to reach to the sink. This way we can reduce the delay, so the in number of hops to the sink. So in order to avoid the loss of data by that is generated or collected by this lower level sensor nodes of cut vertex, so we are going to use AUV to explore the network and identify the cut vertex. Then we use Chapman-Kolmogorov equation to predict the future residual energy of the cut vertex, and we create a priority list. So whichever node is going to die soon will be the higher in the priority list, on the top of the priority list. So we follow AUV follow the priority list and reach near to the each cut vertex, then collect the data instead of cut vertex, while this cut vertex harvests the energy through energy harvesting. So this is the basic idea of our paper. So this proposed protocol is divided into two phases. So in first phase and first subphase, which is network exploration and cut vertex dissection phase, the AUV moves in a land mover pattern to collect the information. So AU doesn't have any knowledge of anything except the area of the deployment. AUV collect ID, level, and location and neighbor list of the sensor nodes. Well, it will check what are the higher level nodes of the neighbor nodes. So they list the higher level neighbor nodes. From that, if there is only one higher level node present in the neighbors list, that will be the cut vertex. That's how AUV identifies the cut vertex. Once AUV identifies the cut vertex, it creates a list of identified cut vertex. So now, as we know that speed of AUV is very slow, so it takes certain time to reach the cut vertex to collect the data from its lower level nodes. So the AUV should arrive at the cut vertex before cut vertex drained its energy. Otherwise, the data collected by the cut vertex and its lower level nodes will be lost. So to predict the cut vertex future residual energy of the cut vertex, the AUV first uh, go to each cut vertex in the list and collect the information such as state and transition probability matrix, which is using Markov chain models. So here states are nothing but as we know that sensor nodes consume energy depends on what state they are in, and for each state the energy consumption will be different. So here uh, our three states that we considered are listening, sending and receiving states. So the AUV then uses this Chapman-Kolmogorov equation to predict the future cut vertex energy in some pi time slots. So expected energy consumption value is calculated using equation 1, equation 2 and equation 3. And here n are the total number of states, which are 3 in our proposed protocol, and energy EJ is the energy consumption by the cut vertex in any state j per time slot, which means in that future time slot what state it is in and what is that energy consumption. With all these details, we can able to find the future residual energy of the cut vertex at pi time slot can be calculated as E residual energy, and which is equals to initial energy, which is the initial energy of this underwater sensor node minus the energy that is calculated in pi time slots. So we subtract and we'll get the residual energy, future residual energy in future by using equation 4. Let's this AUV creates a priority list of the cut vertex by considering this pi threshold, which is pi THR, which is nothing but the time slot in which residual energy of the cut vertex falls below the given threshold energy. So the CUVs are ranked in the ascending order of the pi threshold values, with those having the least pi threshold value assigned to the higher priority. So once it has AUV has the priority list, it then calculates the time that is required to reach that higher, the top priority cut vertex from the current location. So by using equation 5, by using this equation 5, it calculates the time it is required to reach the location. So once it has the priority list, AUV starts visiting the priority cut vertex as in following the priority list. It starts its journey to the first cut vertex, the highest priority cut vertex. Uh, it as it reached near the cut vertex, where the lower level nodes of that cut vertex are in the communication range of AUV, it stops there and it collects data instead of cut vertex, while that cut vertex will be harvesting energy from the installed sea turbines, underwater sea turbines. So while this cut vertex is harvesting its energy, AUV will be collecting the data from the lower level sensor nodes of the cut vertex. This way we are going to stop cut vertex to die, and we are also improving the network lifetime. And this residual energy of the cut vertex can be updated as residual energy that it already has plus the energy that is that can be harvested during the AUV collecting data from the lower level sensor nodes. And these are our simulation parameters. As you see, this data rate propagation speed is 1500 meters per second. Initial energy of the sensor nodes are 10 kilojoules, and 2000 joules is our residual energy threshold for cut vertexes. So the results that we have generated are network lifetime and delay. First of all, we see the network lifetime, and we are comparing our proposed protocol with the stratification based data communications scheme, which is SDCS, and QTAR, which is Q learning based topology aware routing protocol. Here average network lifetime is not for the whole network, but the average network lifetime of the cut vertex, and duration that the cut vertex actively engages in the routing process. This is how we calculated this average lifetime of the cut vertex. So we can observe that the proposed protocol improves the network lifetime of the cut vertex. This is because in the proposed protocol, the AUV can predict the future residual energy of the cut vertex, and it can prevent the cut vertex from dying. So furthermore, when the AUV performs the data collection, the cut vertex harvests the energy and it extends the cut vertex lifetime. But as see compared protocols, which are they are incapable of preventing the death of cut vertex. So this way the lifetime of the cut vertex will be shortening. So furthermore, as the number of nodes increases in the network, the cut vertex has to forward more data, resulting in the increased consumption that leads the faster death of cut vertex. And this red one is our proposed protocol. As you see, it is performing well compared to other protocols. And another result is the delay, which is calculated as average time interval between generating and successfully delivering a data packet to the sink. Here, compared to the other two protocols, the proposed protocol exhibits a lower delay because sender selects the next hop forwarder from the higher level sensor nodes, which are closer to the sink. So it takes less hops and reduces the delay. Additionally, the AUV temporarily collects and delivers data from the cut vertex to the sink in this approach. So this way, this proposed protocol has less delay compared to the other protocols. And if you take QTAR, it experiences more delay, as in QTAR, isolated group members enters in sleep mode, and if they don't receive an acknowledgement, it keep on sending the packets, and it increases delay, and isolated member nodes only wakes up from the sleep mode and rejoin the network when the new transmission is heard. While in SDCS, AUV alone collects the data, causes more delay than QTAR and the proposed protocol. The proposed protocol improves in both lifetime of the cut vertex and in terms of delay compared to other two protocols. In our future work, we would like to analyze the packet delivery ratio and total network lifetime. And these are the references. Thank you.